Welcome to the Deep Dive, the place where we take the most complex technical specifications, the most arcane research papers, and distill them into the knowledge you need fast.
Right.
I'm your host, and today we are crawling under one of the biggest, grittiest, and I think most fundamentally overlooked pieces of equipment on the road.
The vocational heavy-duty cement mixer.
Exactly.
It truly is the unsung hero of industrial electrification.
Yeah.
I mean, when the conversation turns to electric vehicles, everyone focuses on passenger cars or, long-haul semi-trucks.
Right, the flashy stuff.
But the cement mixer, which combines heavy-duty mobility with continuous mission-critical mechanical work, it presents some of the most punishing and complex engineering challenges out there.
It really does. So our mission today is to break down the highly specific engineering roadmap for transforming this noisy beast into a P2 hybrid architecture with an electrified power takeoff the ePTO.
Right.
We are diving deep into the nervous system of this conversion,
Actually,
the critical 24-volt, 400-volt power electronics, and all the logic that governs them.
we're essentially building the technical specification for the integration team from the ground up.
Let's start with the core problem, the whole reason for this multi-million-dollar investment.
It's stunningly simple, really. It's efficiency waste. Traditional mixers waste a massive amount of fuel just burning diesel to idle.
I saw a figure, something like 40%.
Over 40% of their operational time is spent stationary, just keeping that massive drum turning so the concrete inside doesn't set.
Wow.
So you have the diesel engine idling high, burning fuel really inefficiently just to deliver maybe 20 or 30 kilowatts of mixing power to the drum. It's just unnecessary emissions, noise, and of course cost.
And the P2 hybrid plus the ePTO architecture, that's the strategic modern solution to this.
It is. By positioning the electric motor, the P2, between the engine and the transmission, you get hybrid propulsion. But, and this is the important part, you completely decouple the mixing drum from the internal combustion engine.
That decoupling is the game changer.
It is. The drum can now spin silently, efficiently, powered directly by the high-voltage battery,
Especially when the truck is just sitting there at the job site.
or waiting in traffic. The diesel engine is no longer required to babysit the concrete.
So our deep dive today, following this technical architect's roadmap, is going to focus on the non-negotiable engineering requirements.
Yes, the technical specification for the critical interface components.
So we're talking the DC to DC converter, the high voltage harness layout, the HV junction box, and the VCU power coordination logic.
We're defining the system's safety and reliability from first principles.
Okay, let's unpack this, starting with the foundational architecture.
We have to begin with the dual voltage platform. Any large electric vehicle requires these two distinct electrical worlds living in harmony.
First, you have the 400-volt DC high-voltage bus. This is the muscle.
Precisely. The 400-volt bus carries all the heavy energy flow. It connects the large traction battery pack, the P2 motor for propulsion, the ePTO inverter driving the drum motor, and crucially, the input side of our DC-DC converter.
All the heavy lifting happens there.
All the propulsion and heavy vocational work energy, it resides on that bus.
And then running everything else, you've got the 24-volt DC low-voltage bus. That's the brain and the senses of the truck.
Correct. The 24-volt system powers everything that is safety critical for control and operation.
So that's the vehicle control unit, the VCU, that manages the hybrid logic.
The battery management system, the BMS, all the exterior and cabin lighting, the dashboard.
And crucially, things like hydraulic steering assist pumps and air braking systems.
The absolute essentials.
And this is where the system integration challenge really surfaces, isn't it? It leads to the first key insight.
It does. The 24-volt system's ability to sustain control and safety, especially when the main diesel engine is commanded off for efficiency.
Like when it's stationary mixing on battery power.
Exactly. In those moments, it relies entirely on the DC-DC converter to step down power from that 400-volt bus.
Which means a failure of the DC-DC is not a convenience issue.
No, it's an immediate, life-threatening functional safety hazard. If that DC-DC fails, the VCU and all the control systems eventually lose power.
And you lose monitoring, you lose steering assist.
Just everything. You end up in a non-safe state for the vehicle. This risk profile immediately elevates the DC-DC function to a safety-critical component.
So that sets the stage perfectly. The fundamental difference between designing a car and designing a vocational vehicle like the cement mixer is that the design isn't driven by market appeal.
Not at all.
It's driven by the environment and, as we'll see in Section 1, by stringent regulatory compliance.
That's absolutely correct. This truck is not destined for a clean showroom. It operates globally in the absolute harshest environments.
We're talking vibration from constant use.
Chemical exposure from concrete additives, aggressive truck washdowns, and extreme temperatures ranging from Arctic cold starts to desert operations.
So the design specification, it has to harmonize these complex international standards all at the same time.
It's non-negotiable. Let's start with the European and UN ECE standards, specifically ECE R100 Revision 3. This is really the global foundation for high-voltage vehicle safety.
And it defines high voltage HV as anything over 60 volts DC.
Or 30 volts AC, yeah, which puts our entire 400-volt platform squarely into the high voltage, or Class B category. And the latest revision, Rev 3, has dramatically increased the stringency.
Especially around the battery pack, the RESS.
Yes, the rechargeable electrical energy storage system. The focus is on thermal safety, which is paramount when you're handling 400-volt batteries under heavy load on a hot construction site.
The big fear is thermal propagation.
The standard and related national standards like those in China require that even if a single cell enters thermal runaway, a cascading internal failure, the pack has to be designed to withstand catastrophic failure.
Meaning no external fire or explosion.
Right, for at least 5 minutes. This 5-minute window is the non-negotiable legal escape time required for the driver and anyone nearby to safely vacate the area.
And beyond the heat, there's just the sheer mechanical abuse a heavy-duty mixer endures. The truck itself is a giant vibration generator.
Which is why ECE R100 Annex 9A lays out these extreme environmental testing requirements.
Yeah.
This isn't just a gentle shape test. Yeah. It mandates a rigorous sinusoidal vibration sweep from 7 Hz, which is the low-frequency rumble of a heavy diesel,
All the way up to 50 hertz.
which covers high-frequency road input and then back down again repeated 12 times over 15 minutes in the vertical orientation.
That sounds like you're simulating years of brutal road conditions in just a few minutes.
That's exactly what it is. Any solder joint, any harness clip, any internal component mounting in the HVJB or the DC-DC that isn't perfectly designed and secured will fail this test.
So if the design team wants this truck to last a standard 7-year commercial duty cycle,
Then Annex 9A vibration requirement is the gatekeeper, period.
and the temperature cycling is just as unforgiving, I imagine.
Not at all. The standard demands component survival through thermal shock simulations.
So rapid transitions between extremes.
Yes, between minus 40 degrees Celsius and plus 60 degrees Celsius, within 30-minute intervals. This rapid shift tests the integrity of seals, potting compounds, material coefficients of expansion.
If a sealant around a cable gland cracks during that 100-degree swing,
Moisture ingress is guaranteed, and that leads to electrical failure. It's a simple cause and effect.
Okay, now let's cross over to the Chinese GBT standards. Here, the focus really sharpens on electrical isolation and physical durability.
Which are two massive concerns for construction vehicles, right?
Absolutely.
So GB 18384 2020 is our foundation for HV design in the world's largest commercial vehicle market. And the central architectural mandate is unwavering, mandatory electrical isolation.
The high-voltage system has to be galvanically isolated from the truck chassis and the low-voltage ground.
Non-negotiable for safety. And this isolation isn't static. It has to be actively monitored.
This is where the insulation monitoring devices, the IMDs, come in.
Absolutely. Mandatory integration. And the standard specifies a very strict alert threshold. For a DC circuit, the isolation resistance must be greater than 100 ohms per volt DC.
Let's translate that into the real-world consequence for our 400-volt system.
Well, 100 ohms per volt times 400 volts. That brings the alarm threshold to 40 kiloohms.
Below 40 kiloohms and alarm triggers.
Precisely. If that isolation resistance drops below 40 kiloohms, it means enough leakage current, we're talking tens of milliamps, is flowing to contamination pathways.
Like wet cement dust or dirt or moisture?
Exactly. And that presents an immediate life-threatening shock risk to a worker who might be touching the metallic chassis. For the VCU, this is a non-negotiable hard stop. The system must immediately command isolation and fault.
So that 40 kelvin limit is a critical, measurable safety target.
It is. And then there's the waterproofing requirement, which makes sense given the constant exposure to concrete and high-pressure washing.
This is where vocational vehicles are just so much tougher than passenger EVs.
Far tougher. GB mandates stringent durability ratings. The components, especially connectors, motor casings, the HVJB enclosure, they must meet IP67, or ideally the even higher pressure rating, IP6K9K.
And IP6K9K is specifically for high-pressure, high-temperature water jets.
The exact reality of cleaning cement off a truck every single day.
Okay, let's pivot to North America and Japan. Here, the focus shifts again, mostly toward rapid post-crash safety and physical standardization.
North America's FMVSS 305 is critical here. It's all about immediate post-crash protection.
Right.
The regulation mandates that in the event of a collision signal, typically from the vehicle's restraint control module, the high-voltage source must rapidly isolate or drop below the safety threshold of 60 volts.
Within milliseconds. That requires incredible speed from the HVJB's contactors.
It demands specialized high-speed contactors and really robust fault detection logic to actuate them. The system needs to de-energize the entire exposed bus within the time it takes for emergency responders to even approach the vehicle.
Preventing electrocution hazards after a crash.
That's the goal.
And Japan provides a non-negotiable aesthetic requirement that's actually a crucial safety mandate.
It is. While Japan's triassembly standards mostly align with ECE safety tests, they strictly enforce the Universal Safety Color Code.
Every high-voltage harness on the vehicle must be RLL 2003 Safety Orange.
It's a procurement specification that cannot be violated. It ensures immediate visual identification of potential hazards anywhere in the world.
And finally, there's a crucial distinction we have to make. This is not just a vehicle, it's also machinery.
Which brings in the European Machinery Directive, a critical regulatory overlay.
Because the mixing drum is defined as machinery.
The ePTO system falls under the scope of the European Machinery Directive 2006/42/EC and its associated safety standard ISO 13850.
Which means the system must have a hardwired immediate emergency stop, the e-stop.
The big red mushroom button on a yellow background, exactly.
And this button has to be connected in a very specific way.
It must be compliant with ISO their 85850, and critically, it must act directly on the ePTO inverter's safety torque off, or STO input.
So the architectural insight here is the need for hardware independence.
Yes. This e-stop cannot rely on VCU software logic, or the operating system's health, or a CAN bus message. It has to be a physical circuit cut that guarantees immediate, absolute power termination to the mixing drum motor, regardless of any software failure.
That regulatory rigor clearly defines the boundaries for component selection. So now let's dive into the component that serves as the indispensable bridge between our two voltage worlds.
The DC-DC converter.
Exactly. This is Section 2, covering key technical point 3.1 and deliverable 0304.
The DC-DC converter's functional requirement is deceptively simple. It's just converting the 400-volt power to a stable, regulated 24-volt supply.
Adjustable between 20 and 30 volts.
Right. But as we established, because it replaces the traditional alternator and it has to operate even when the engine is off, its reliability is safety critical.
And the most crucial safety requirement for the DC-DC in this heavy-duty application is galvanic isolation. Why is this mandatory, not just optional?
Galvanic isolation uses an internal transformer barrier to ensure there is no direct electrical path between the high voltage input and the low voltage output.
Between the 400-volt side and the 24-volt side.
And this is mandated globally because it prevents high-voltage transient spikes caused by motor switching or regeneration or ground fault from propagating across that barrier.
So if the isolation fails,
you risk instantly frying the VCU, the BMS, and all your safety-critical 24-volt electronics. It leads to a total vehicle control shutdown. It's a fundamental protection against single-point failure propagation.
So here's where the architectural design trade-offs emerge. Let's talk topology selection. We often see two main architectures in the 400-volt domain.
The LLC resonant converter and the phase-shifted full bridge, or PSFB, converter.
A classic engineering decision.
It is. It's a choice between ultimate peak performance and sheer robustness. The LLC resonant converter is highly favored for achieving incredible efficiency.
We're talking sometimes exceeding 96% across most of the load range.
Yeah, which is achieved through sophisticated control that enables zero voltage switching and zero current switching, minimizing losses.
That sounds like the ideal choice for a vehicle that's driven by efficiency targets. So what's the hidden cost?
The trade-off is control complexity. LLC converters typically require variable frequency control to regulate the output voltage, especially when the 400-volt input fluctuates.
Which happens all the time in a hybrid system during acceleration or braking.
All the time. And this variable frequency complicates the EMI filtering, and crucially, it makes it very difficult to synchronize and parallelize two or more DC-DC converters for redundancy or higher power needs.
So if the LLC is the high-performance, finely tuned race engine, what is the phase-shifted full bridge?
The PSFB is the heavy-duty tractor engine. It sacrifices a tiny bit of theoretical peak efficiency for rock-solid robustness and simple control.
So it's more stable.
It offers excellent wide-range output regulation across massive input voltage fluctuations, say from 250 volts all the way up to 475 volts DC, which is common. It also uses fixed-frequency PWM, which simplifies EMI filtering and makes parallel operation incredibly easy.
Wait a second, though. We just established that the core mission here is overcoming that 40% fuel waste. Are we really favoring simpler parallel operation with the PSFB over the 96% peak efficiency of the LLC? Isn't that sacrificing the core mission?
That's a critical challenge, and it's a great question. The answer lies in system robustness for this kind of vocational duty. The auxiliary loads in a cement mixer, they're relatively stable overall.
Even with some high transients from pumps or valves.
Right. The ability of the PSFB to maintain perfect output regulation, that stability, and to easily integrate parallel units for redundancy, that gets prioritized over the last percentage point of efficiency.
Because in a construction environment, downtime is catastrophic.
Robustness wins. Plus, by mandating modern components like CTEC or MOSFETs, we can push the PSFB efficiency well over 95% anyway, which mitigates most of that theoretical loss. So the engineering verdict really leans toward the proven, robust, and easily parallelized PSFB architecture for this application.
Robustness over refinement, understood. Now, the DC-DC has to integrate into the truck's central nervous system, the communication network. This is deliverable 0304.
Absolutely. The DC-DC is a smart node. Since we're in the heavy trucking domain, the communication backbone is the North American standard, SAE J1939.
But for systems that need higher throughput.
For those, we recommend implementing the DC-DC protocol using CAN-FD, flexible data rate, for lower latency on critical control messages. Diagnostics are handled via UDS.
How does the VCU actually control the smart node in real time?
The VCU, or the overarching energy management system, doesn't just passively monitor. It dynamically dictates the DC-DC's behavior via the J1939 network. It sends a set point command for the DC-DC's output voltage.
So, for example, in deep winter conditions.
The VCU might command a voltage boost, raising the output set point from 28 volts up to 29, to force a faster charging rate into that cold 24-volt auxiliary battery. It maximizes its state of charge ahead of an engine-off period.
So we need to define the critical J1939 signals, the PGNs, that have to be reported back to the VCU.
We mandate specific high-priority PGNs for status monitoring. Key signals include DC-DC N-Volt, which reports the 400-volt bus health, and DC-D Coke curve, which monitors the actual 24-volt load.
And both of those need a high-priority rapid 10-millisecond update rate. Why so fast?
Because if the 400-volt bus suddenly collapses, say during a high-power ePTO demand event, the VCU has to get that information fast enough to execute a load-shedding sequence or command the engine to restart before the DC-DC drops the 24-volt network entirely.
And finally, the physical interface requirements for this rugged environment.
The physical connections have to meet the standards we defined in Section 1. The HV input must use a 2-pin shielded connector, and critically, it has to integrate the required HVIL safety switch.
The high-voltage interlock loop.
Exactly. The LV output, handling high current, needs robust, sealed M8 threaded studs. And the signal interface demands a sealed multi-pin connector. A 12-pin is standard to carry the TAN and control signals, all while maintaining that IP67, IP6K9K integrity against washdowns.
Okay, we've established the rules and the bridge. Now that we know what components we need, we have to connect them safely, efficiently, and reliably.
Which brings us to Section 3, the nervous system.
The HV harness selection and routing, which is all documented in deliverable 0301.
This is where most field failures occur. The harness is arguably the single most failure-prone component because of that combination of vibration, heat, and chemical contamination. You need mechanical robustness that exceeds the electrical rating.
Let's start with material science and sizing. We know the outer jacket must be RAL 2003 orange. What about the inside?
The conductor must be high-purity T2 copper for flexibility and conductivity. But the insulation is the real battleground. We mandate cross-linked polyethylene, XLPE, or silicone rubber jackets rated for at least 600 or 1,000 volts DC.
And those materials offer better thermal stability and chemical resistance.
Superior resistance, especially against the aggressive cleaning agents and alkali chemicals found on concrete construction sites.
Let's talk about cable sizing. Give us the technical example for the ePTO circuit.
Okay, so our specification requires sizing the cable not just based on steady-state current, but based on heat rise. If the 50 kilowatt peak ePTO motor draws roughly 125 amps at 400 volts, The preliminary size calculation lands us between a 35 and a 50 square millimeter cable.
And the purpose of that is very specific.
It's to limit the temperature rise under peak load to less than 55 Kelvin above ambient.
Why is that specific 55 Kelvin limit so important?
Because if you exceed that temperature rise, you accelerate the degradation of the cable insulation dramatically. For every 10 degrees Celsius you go over the rated limit, you essentially have the insulation's life expectancy.
So if you choose a wire that's too small just to save a little bit of cost,
You are guaranteeing premature dielectric breakdown and a major system failure 4 years into the truck's life cycle. Cable sizing is an investment in longevity.
next up, the critical element of signal integrity and safety, electromagnetic compatibility, or EMC.
EMC is a massive challenge in a hybrid truck. You've got high-frequency switching noise from the P2 inverter and the DC-DC converter running massive currents right next to incredibly sensitive, low-voltage CAN communication lines.
And if that noise couples into the CAN bus,
The VCU starts receiving garbage data, which leads to unpredictable operation or shutdowns.
so what's the mandatory shielding requirement to prevent that?
All HD cables must use a tinned copper braid with a minimum coverage of 85% or more. This braid has to function as a true, continuous Faraday cage containing the noise generated by those pulsed DC currents.
And the grounding principle for that shield is critical. You can't just ground it at one end, can you?
No, you can't. For high-frequency noise, which is what we have here, single-point grounding creates an antenna effect, which actually amplifies the noise.
So the shielding must be grounded at both ends.
At both ends, at the power source, the HVJB, and at the load, the ePTO inverter, using specialized 360-degree EMI back shells. This ensures a continuous low-impedance path to chassis ground for the high-frequency currents.
And that gets you compliance with strict standards like CSPR 25 Level 3.
It does.
Okay, let's move to the physical routing rules, the Builder's Manual, deliverable 03-01. The network topology starts at the HVJB as a star-shaped network. Why?
This star topology ensures that all main power lines originate at one central point, which facilitates fault isolation. If the cable running to the ePTO motor shorts out, the fuse or contactor in the HVJB isolates only that one branch.
Leaving the rest of the system, like the DC-DC and the P2 motor, still operational if possible.
Exactly. Now for the non-negotiable physical routing rules. Rule 1, high-low separation.
HV and LV harnesses must maintain a separation of at least 100 millimeters when they run in parallel.
To minimize capacitive and inductive coupling. And if they have to cross, they must cross at a strict 90-degree angle. This is a primary defense against interference.
Rule 2 addresses the massive vibration problem, fixation.
Cables larger than 16 square millimeters must be secured every 200 to 300 millimeters along their entire length. This prevents dynamic movement and fatigue failure.
But the most critical detail is near the termination.
Yes. The first clip must be less than or equal to 100 millimeters from the connector outlet. This rule is designed to reduce mechanical stress or fretting corrosion on the terminal connection itself.
Which is the leading cause of high resistance points and heat generation inside the connector.
It is. And finally, protecting the insulation from the environment.
The minimum bend radius.
It has to be 5 to 6 times the cable's outer diameter. Bending it too tightly stresses the insulation, creating micro cracks that can lead to dielectric failure over time.
And you have to avoid heat sources.
Strictly, greater than 200 millimeters from exhaust manifolds, or you have to use 500-degree thermal sleeves if you can't avoid it. And you have to rigorously check routing against the dynamic envelope space.
Making sure the cable isn't crushed or pinched when the cab tilts for maintenance.
For instance, yes.
If the harness is the nervous system, then the high-voltage junction box, the HVJD, has to be the heart. It controls the flow and ensures safety.
That's a good analogy.
So we're covering deliverables 03, 02 for fuses, 03, 03 for contactors, and 03, 05 for the HVJB interface data.
The HVJB is the central brain and distribution center. It contains all the essential components, the contactors for switching, fuses for protection, current sensors, and that critical high-voltage interlock loop safety chain.
Let's start with the physical design. It has to be robust inside and out.
It's mandated to be a die-cast aluminum enclosure, maintaining that IP67, IP6K9K rating against dust and high-pressure water. Inside, power distribution relies on nickel-plated copper bus bars.
And the specification limits the current density on those bus bars to a maximum of 1.3 amps per square millimeter.
It does.
Why that specific number? It seems very conservative.
It's a heat management strategy, and it's tied directly to reliability. If you exceed that limit, the localized temperature rises too high.
And that causes failures.
Two critical failures.
Yeah.
First, it accelerates the aging of the busbar insulation or standoffs. Second, it creates localized hotspots that can degrade the performance of nearby components like fuses. So maintaining a low current density is paramount for the 10-year life expectancy of the HVJB.
Inside the box, we have the most critical spatial regulations: clearance and creepage.
These are non-negotiable safety distances, especially crucial in a polluted environment like a cement mixer. Clearance is the shortest distance through the air.
And creepage is the shortest distance along the surface of an insulator.
Exactly.
And the required minimums for our 400-volt system.
We mandate clearance, the air gap, must be greater than or equal to 4 millimeters.
Right.
And creepage, the surface distance, must be greater than or equal to 8 millimeters.
Because if cement dust or moisture bridges that gap.
The pollution degree is high. If that creepage distance is too short, the contamination creates a low-resistance path, leading to tracking, or, worst case, an immediate flashover. These distance rules are the physical manifestation of that 40-coulomb isolation rule we talked about earlier.
The ultimate physical safety feature within the box is the HVIL.
The high-voltage interlock loop. It's a continuous, low-voltage, hardwired circuit that acts as a physical security chain. It daisy-chains through every high-voltage connector and includes a switch on the HVJB lid itself.
So if any part of that loop is broken.
A connector is loose, the lid is opened, the HVIL circuit instantly reports a fault to the VCU.
And what's the consequence of that fault?
The VCU must instantly and irreversibly command the main contactors to open, completely de-energizing the HV system. This ensures maintenance staff can't accidentally contact a live circuit. The HVIL check is step 2 in the VCU's power-up checklist.
Okay, let's move to the contactors. These have to interrupt 400 volts DC, which generates massive destructive electrical arcs.
They require specialized technology. Standard relays will instantly weld their contacts at 400 volts DC. We mandate ceramic-sealed, gas-filled contactors.
Usually a hydrogen-nitrogen mixture.
Yes, which are designed specifically to rapidly cool and extinguish that high-voltage DC arc when the circuit is interrupted. It prevents catastrophic failure and contact welding.
And the life cycle has to match the truck's operational frequency.
The spec demands a minimum of 100,000 mechanical operations. And to manage the thermal budget and save energy, the contactors must use economized coil circuits.
So the VCU only applies a high current pulse to pull in the contactor.
And once it's latched, a PWM-based circuit reduces the holding current drastically, which saves power and reduces coil heat.
This brings us to the pre-charge circuit logic, the gatekeeper that prevents the system from destroying itself on startup.
This is an absolute necessity. Without it, closing the main contactors would dump the full battery voltage onto the massive uncharged DC link capacitor banks in the inverters,
Creating a huge inrush current, thousands of amps.
which would instantly destroy the main contactor contacts through electrical erosion and welding.
So the VCU has a precise sequence to avoid this surge.
It's non-negotiable. First, the VCU closes a smaller, lower-rated pre-charge relay, which is wired in series with a power resistor.
And that resistor limits the current to a safe level.
It does, allowing the DC link capacitors to charge slowly. The VCU monitors the DC link voltage, and only once that voltage reaches 90 to 95% of the battery voltage.
Which means the charge is complete, usually in under 500 milliseconds.
Only then can the VCU safely close the main contactors, and the pre-charged circuit is then immediately opened.
Okay, next, fuse selection. We're not just protecting the copper wire here.
No, we're protecting the semiconductors.
Yeah.
This is the expensive part. The fuse has to protect the expensive IGBTs or MOSFETs inside the inverters.
So the fuse's I2T curve, its thermal melting characteristic.
It has to be perfectly coordinated to sacrifice itself before the destruction energy threshold of the $20,000 power module it's protecting is reached. That coordination is a critical system safety study.
And this protection calculation is far more complex than just calculating max current. You need deep rating factors.
The rated current calculation for a heavy vehicle is rigorously die-rated. The core formula is the RMS load current, divided by a whole series of factors.
And for the cement mixer application, 2 factors are absolutely critical.
The first is K sub T, the temperature derating factor.
Yeah.
It's typically 0.7 to 0.8 because the fuse is operating inside a hot HVJB enclosure.
And the second critical factor.
K sub C, the cycling load factor. Often between 0.6 and 0.7, the cement mixer drum is constantly reversing, starting, stopping, which creates thermal cycling on the circuit.
And that cycling induces thermal fatigue on the fuse element itself.
Exactly. If you don't use KCE, the fuse will fail prematurely from thermal stress, not an electrical fault, causing expensive, unnecessary downtime. Applying these de-rating factors ensures the fuse lasts its expected service interval.
What type of fuse do we mandate for the ePTO motor circuit?
Because we're protecting sensitive, expensive semiconductors, we mandate high-speed semiconductor fuses, so an AR or GR class. Their interrupting capacity has to be massive, exceeding the battery's worst-case short-circuit current,
10,000 amps or more.
at least. And their rated voltage has to be 500 or 800 volts DC, higher than the nominal 400, to safely suppress the huge voltage spikes generated when the motor regenerates power back to the battery.
We've specified every component down to the safety distance. Now we move into Section 5, the brain.
This is the VCU power coordination and functional safety logic, key point 3.3.
This is where all those robust components get managed intelligently.
The vehicle control unit is the conductor of this orchestra. It runs a complex state machine, starting with the power-up sequence, ensuring component safety before allowing any high power.
Give us the VCU's mandated power-up checklist.
Okay, step 1. VCU wake-up. Triggered by the ignition key or external charging.
Step 2.
HVIL check. The VCU verifies the physical continuity of the high-voltage interlock loop. If that loop is open, it registers an ASIL-D failure and stops the sequence right there.
Then the isolation check.
Step 3, yes. The BMS reports the IMD status, verifying the isolation resistance is above 40 k ohms. Then step 4 is the pre-charge phase.
The VCU commands the pre-charge relay closed, initiating that current-limited charging.
Great. And finally, step 5, the ready state. Once the DC link voltage matches the battery voltage, the VCU closes the main contactors, opens the pre-charge circuit, and enters the ready state.
That checklist ensures a safe start. But once it's running, the power arbitration logic is the survival instinct. If the battery SOC is low and the driver is demanding full ePTO torque, how does the VCU decide where the power goes?
In a cement mixer, the power priority matrix is unique. It's dictated by non-negotiable safety and, crucially, by concrete integrity.
Losing the mix means destroying thousands of dollars worth of product and potentially damaging the truck.
Exactly. So priority 1, the highest priority, is safety-critical steering and braking and the ePTO mixing drum.
The motor has to maintain a minimum rotational speed of 1 to 3 RPM.
The survival speed. It prevents the concrete from setting or segregating. This is power that cannot be compromised.
Okay, priority 2.
The DC-DC converter. As we established, a DC-DC failure leads to a complete loss of the 24-volt control network. So maintaining 24-volt power for the VCU and BMS is essential.
It takes precedence over comfort and even thermal management.
It does. Which brings us to priority 3, battery thermal management, cooling or heating the battery to keep it in that optimal 20 to 40 degrees Celsius range.
And the lowest priority is the comfort load.
Priority 4, cabin HVAC and the PTC heater. This is the first load the VCU must shed during any high-demand event. It'll shed the AC compressor to maximize available torque for the P2 motor during an uphill acceleration, for example.
And what happens if the battery sock dips below the operational minimum required to sustain priority 1, the mixing drum?
The VCU executes the engine start strategy. It commands the internal combustion engine to immediately start, not for propulsion, but to act as a stationary generator.
So the P2 motor switches instantly to generator mode.
It uses the ICE's power to recharge the HV battery, ensuring power continuity for the critical ePTO load and replenishing that sock margin.
This level of complexity requires adherence to functional safety standards, like ISO 26262. We have to assign ASIL grades.
The automotive safety integrity level, yes. The grade determines the rigor, the fault tolerance, redundancy, the whole development process required for a component. It's based on severity, exposure, and controllability of potential failure modes.
So let's look at the highest risks specific to a mixer truck.
The most dangerous scenario, demanding the highest integrity, is the P2 motor generating unexpected torque during driving.
If the truck suddenly and unintentionally accelerates on the highway,
The severity is high, a potential major accident, and the controllability by the driver is low. That clocks in at ASIL-D, the highest integrity requirement.
how do you architecturally mitigate an ASIL-D fault? It requires more than just one VCU checking itself.
Absolutely. Achieving ASIL-D demands diverse redundancy. This means the primary VCU can't be the sole monitor. We mandate a physically separate, independent safety microcontroller.
A safety island or monitor.
Yes, that constantly checks the primary VCU's commanded torque versus the actual motor output torque, often using a completely different sensor path and calculation methodology.
So if the primary VCU software fails and commands 100% torque when 0 is commanded.
The safety monitor must immediately trip the safety path, the STO, forcing the motor to 0 torque.
And what about the machinery hazard?
The ePTO accidental start during maintenance or cleaning, that's another high risk. The potential for severe injury while a worker is inside the inspection hatch warrants an ASIL-C rating.
And the mitigation is an independent mechanical safety lock?
A hardwired limit switch on the inspection hatch must physically cut the current path to the ePTO module, independent of the VCU software. It's a crucial hardware lock against software failure.
And the DC-DC failure we discussed earlier.
Loss of 24-volt control due to DC-DC failure is managed at ASIL-B. While critical, the severity is slightly lower than unexpected propulsion torque.
It often results in a controlled shutdown rather than uncontrolled operation.
Exactly.
What's the ultimate mitigation strategy when a high-power component like the ePTO module begins to overheat? Do we just shut it down?
For almost any other vehicle, a high-temperature fault results in an immediate shutdown. But for the cement mixer, a complete shutdown is catastrophic because the concrete will set.
So the VCU has to be smarter.
It implements a nuanced fault degradation strategy. If the ePTO module overheats, the system should derate limit the output torque rather than shut down completely.
Limiting the torque, say, to 30% of maximum.
It allows the drum to maintain that critical 1 to 3 RPM survival speed. This buys the driver time to reach a safe location and empty the load, preventing financial loss and truck superstructure damage.
We have defined a rigorous, safe, and robust 400-volt P2 hybrid architecture. But as technical architects, we also have to look forward. Section 6. What are the key emerging trends that will shape the next generation of electrified mixers?
The industry is already planning the architectural jump to the 800-volt platform. While 400-volt is mature today, 800-volt is the future standard for heavy-duty applications.
What's the main driver for that shift?
It's physics. Doubling the voltage halves the current required to deliver the same power.
And lower current allows for thinner, lighter, and cheaper HV cables.
A substantial vehicle weight reduction. But it's a major engineering hurdle. That higher voltage dramatically increases the requirements for electrical safety. We would need larger creepage and clearance distances, potentially increasing the size and cost of the distribution components.
And the components themselves are getting smaller, thanks to material science.
Absolutely. The mass adoption of wide bandgap semiconductors, specifically SUS, silicon carbide, and eventually GaN, gallium nitride, is changing the game.
They handle heat better and allow for much higher switching frequencies.
Which means smaller required inductors and transformers, leading to more compact, higher-density power electronics that fit better into the tight chassis space of a mixer truck.
Beyond hardware, the software intelligence is also rapidly increasing.
Predictive energy management is the next frontier for optimization. By integrating GPS data, road topography, and traffic conditions, the VCU can become proactive.
It can optimize the battery state of charge dynamically.
So, for example, it can ensure the battery is charged strategically before the truck arrives at the high-load discharge job site, guaranteeing maximum electric power availability for the ePTO without needing to run the ICE.
And finally, capitalizing on that large battery pack for utility.
We're seeing the necessity of bidirectional DC-DC converters. They allow the vehicle to not only step down 400 volts to 24, but also to act as a mobile power source.
Vehicle to load, or V2L.
Exporting power for construction site tools, lighting, or emergency services, leveraging that massive energy capacity stored in the HV battery pack.
We started this deep dive with the goal of generating the specific engineering toolkit required for the integration team. So let's summarize the 5 key deliverables derived from this specification.
Okay, these 5 documents are the output of our architectural review. First, 0301, the HV harness layout.
This defines the physical reality, the 3D routing, fixation points, the 100-millimeter separation rule.
And the critical sub-100-millimeter clip rule for terminal stress relief. Second is 0302, fuses selection.
The detailed protection coordination study proving the I-squared-T characteristic is matched to protect the inverters.
And incorporating the essential derating factors like KT for temperature and KC for cycling load. Third is 0303, contactor selection.
The technical requirements for the ceramic-sealed, gas-filled contactors, and the finalized, safe, sequential pre-charge logic.
Fourth, 0304, the DC-DC interface data. This details both the electrical interface and the logical specification.
The full J1939 DBC file, with all the control set points and PGNs mandated at that 10 millisecond update rate.
And finally, fifth, 0305, the HVJB interface data, the master schematic detailing the internal bus bar design and strict adherence to creepage and clearance minimums.
So this transition to an electrified, heavy vocational vehicle, it's not just an environmental obligation, it's a strategic systems engineering problem.
It is.
And by defining this 24-volt, 400-volt architecture with absolute rigor enforcing safety via the HVIL and mandatory isolation, and ensuring durability through these specifications manufacturers, are fundamentally redefining the efficiency and reliability of the commercial fleet.
The complexity demands that every subsystem acts as a hostage to the safety of the entire architecture.
Which leads us to our final thought for you to consider. We spent time analyzing the $20,000 IGBT modules, the huge battery pack, and the 50-kilowatt motor.
Big-ticket items.
Yet the entire system's ability to even safely power up and begin operation hinges on the smallest, cheapest subsystem we discussed, the pre-charge circuit.
A single resistor and a relay.
So what other seemingly small ancillary systems in these high-stakes, high-voltage environments are similarly holding the entire complex architecture hostage, demanding equal redundancy and precision just to execute the most basic function?
That is the real challenge of architectural design.